thanks a lot for coming to my talk on 3D audio. So I assume that most of you are actually working in VR and do work in some way or another with audio as well. Otherwise, you would probably not be here. So the question is maybe just to get an idea in the beginning, what things are you familiar with? Who of you is familiar with HRTFs? One person? Don't worry, I will explain what it is. So, who of you uses some platform like Unity or so that has and uses there the built-in 3D rendering, like Unity, Steam, whatever they? No. Okay. Even better. I will explain you what my approach is to this field, and it's a bit different from what is presented already in some of the platforms that are on the market. So let me, before I go into the details of this topic, let me introduce myself a little bit. So my name is Fritz Menzer, and I've done my first degree in physics. So I have some relationship with acoustics, but then continued more to the signal processing side in the field of communication systems at EPFL, which is kind of the local technical university here in Lausanne. And I've been since then kind of switching between academia, art, and industry. So I was a teacher at the University of Art and Design in Lausanne in the Media and Interaction Design department. Then I went back to academia. I did a PhD on binaural audio signal processing. Then I actually started my startup, Ambient signal processing, but did not work for very long at 100% for that, but went back to the industry actually at 60%, and 40% I continued developing my signal processing algorithms. And then I even went back to academia and I did a postdoc in Munich on the perception of reflections in rooms. And well, since a year and a half now I'm working full-time on MNSP, and I've been doing different projects within the framework of MNSP. It all started in 2010 with a sound decorrelation algorithm for setups with a really high number of loudspeakers. Think like 100 to 400 loudspeakers. And if you want to make a nice diffuse sound field, you should actually have signals that are decorrelated on these different loudspeakers. And I worked on an efficient algorithm for implementing this decorrelation. It was the first thing I worked on. And since then, I've been in different projects, mainly to be sold as apps on the App Store. There are synthesizers, the latest ones, Chromium and DA1, which is a digital analog hybrid synthesizer with 38 oscillators. And also in generative music, again, Chromium, which is kind of a simple app where you just put your fingers on and it starts making music. And Logic Analogic, which actually originally comes out of the activity at the art school in Lausanne, which is basically a circuit. It's a simulation of a circuit that generates music by itself. And last but not least, the latest project I've been working on for the last year or so is a binaural rendering algorithm, which is basically already the third binaural rendering algorithm I'm working on, and which is based on my research both in Munich and in Lausanne, which was both partially perceptual research on what is important in 3D audio, that it sounds right. And I'm using this knowledge now to make algorithms that are really efficient and sound well and sound better than some things which are maybe even more physically correct. So here is the outline for this workshop. I will first talk about the motivation for using 3D audio, also the motivation for actually doing it right, not doing it the cheap way. Then I think the longest part of it is actually the background in acoustics. So I suppose for you working in virtual reality, certainly knowing the visual aspects of virtual reality well, it's interesting to know also about the auditory aspects, which have their own physical elements to it, their own perceptual elements, which things are important and which things can we just model in a very simple stochastic way. Then I will, of course, present you what my 3D verb algorithm actually does and how it addresses these issues that I identified. Something is stopped. Great. And so I will explain you how it addresses the issues I've identified during my research. And then finally, I will talk also about different implementation philosophies and how you can approach 3D audio in different ways. And of course, my way is one of different possible ways. I hope I can convince you that what I'm doing is kind of a good compromise between different extreme ways. And last but not least, just for fun, I want to talk also about 3D audio as a modality of virtual reality on its own. So if you don't have the VR goggles, you can still do virtual reality, but it's just for the ears. And I think of course, it's a niche. It's not by far not as big as visual virtual reality, but it has some interesting applications. So I just want to mention this concept as well. Yeah, and then there are some conclusions if we still have time. So why should you make an effort to actually implement a good 3D audio synthesis in your VR applications? Well, on one hand, it's just a natural extension, right? I mean, you're doing all this effort to make your environment visually attractive and congruent and pleasant, just. So why not do it also on the audio side? And there's something that I want to mention because from what I've seen here and in many other places in virtual reality, it seems to be the standard, but in my opinion, it's super weird. Imagine you have some virtual reality scene, let's say in a game, and you have some game music. I mean, most games have some kind of background music because it helps you have this ambient and kind of get the mood of the game through the music. Now, usually what is done is that there is some sort of spatialization, there is some sort of 3D audio used for the individual sources, like doors opening and closing, monsters coming towards you, fights and so on. These are normally spatialized, if people made that effort at least. But I've so far never seen any spatialized music. So what you actually have there is a superposition of a more or less natural scene with sound sources outside your head that you can localize, and some music which actually plays in your head, which is as if inside the game you were wearing headphones, but that still let the sound come through. It's really, if you think about it, it's quite a weird situation. I would say, even for background music, think about 3D audio as well. It's just a natural way to do it. How you want to implement it, of course, is a question of what kind of scenario you're working on. If you can imagine some kind of band playing somewhere and then have the sounds localized there and fade in and out as you come closer to the band and move away. Last but not least, actually, the 3D audio, even though maybe, well, of course, the visual mode is the most important. It dominates everything. But on a more subconscious level, audio is very important, and particularly, it can help modulate the comfort level of people. So normally in nice sounding environments where you hear a room that is reasonably big and so on, you actually feel comfortable. if you're in an environment where everything feels very cramped and you have the impression that everything is close to you just because of the environment, you feel less comfortable. So it's something you can actually use consciously to make the people more comfortable or make the people less comfortable if you want that. So just to illustrate this a little bit, I'm sorry I didn't update the graph. So this is basically for let's say a game that is played on a tablet rather than with VR goggles. But to some extent, the issue is the same. Oh wow, now this is not visible at all. But basically, what you normally want is that the person playing the game actually thinks. So this is a big thought bubble with some nice environment with a river and forest and so on. So the person wants to, the developer, as a developer, you want that the user has the impression of being inside that environment. But what you normally get is that, well, this environment, well, it's the same environment again, but it's not really visible. With the sounds themselves, you evoke that environment, of course. You have the water flowing, you have the wind in the trees and so on. But if it is not properly spatialized, you just evoke the concept of the environment, but the person is not in it. Now, of course, this applies less to VR in the sense that you actually show the environment. The people look up, there are the trees, down here is the river, and I hear the river, so maybe the brain, even if it's not properly spatialized, the brain associates the sound of the water with what is shown with the goggles. But still, if you don't do this spatialization properly and the environment modeling properly, you actually give the user a sort of cognitive dissonance. Because if you have, in the extreme, you have a stereo representation of your environment, which is basically all in the head, and you show the environment outside. If you close your eyes or you open your eyes, the impression is completely different. So, yeah, be aware of this cognitive dissonance that you're actually creating with spatialization that is not properly done. So that was my motivational part. Now let's come to the technical side. So what is important if you want to do 3D audio correctly? Something that at least one person here is familiar with is hrefs, and they are really the basic building blocks of 3D audio with headphones. Of course, you can also do 3D audio with tons of speakers, but I'm focusing here on headphones because anyhow, that's normally what you're doing with virtual reality. So a head-related impulse response or head-related transfer function, basically they're the same thing, just if you look at the time domain or the frequency domain, is basically the signal that you get if in an anechoic environment, like imagine anechoic chamber or like a big open field, if in such an environment you have a sound source that emits a perfect impulse, like something like a balloon popping but more perfect, and you record the signals that you get on the left ear and the right ear, and the signal that you get is shown there on the screen, about 3 seconds long, and it contains all the information that is due to the interaction between that sound wave and the head of the listener. And it looks like not much, to be honest. It's a pretty simple signal, if you like. But these signals are actually individual. So from one person to another, they slightly change. And they really encode with a certain degree of reliability the positioning of the source relative to the head. So if you place a source here, you get a different signal than if you place a source here, or you place a source above the head or behind the head. These signals, they change. And by applying these impulse responses to some source signal, you can actually already place a source relative to the head. It's mostly a directional information. There is very, very, very little distance information contained in it. Basically, the distance information only appears when the source is really close to the head. Otherwise, it's just a direction that is given. But this is really the basic building block that you need in 3D audio. Did I explain this sufficiently well that you understood the concept? Great. So let's move on to the next thing. And that is, and remember, these signals, they're like 3 milliseconds or less long. So really short time frame from the arrival of the sound wave until the last oscillation happening inside the ears. Let's go to room acoustics. So if you have a sound source that emits a signal, I hope I can, I don't know, it doesn't seem to work, but well, look at the left side of the slide. You see there basically a black circle that is already reflected on some walls. That represents the original signal that is emitted from a sound source inside the room. So you can imagine how this evolves. So it's reflected and reflected again and so on. And you see what is happening in the room at 5 milliseconds, 12 milliseconds, 30 milliseconds, and basically 80 milliseconds and greater. It's just a mess. You don't find much structure anymore in it. And what is represented there visually actually corresponds also to what we perceive. So in the beginning, you have this direct sound coming, then you have some reflections from the ceiling, from the floor, from different walls. In the beginning, these are all relevant, they're all important. Later on, when you have this big mess, it's still relevant that you have this mess, but the fine structure of it, we cannot perceive it. That was part of my research at EPFL. If you basically replace the signals that you measure after 80 milliseconds for a room about this size here, it doesn't matter what the fine structure is. You can just take some artificially generated noise and filter it properly that the statistical properties are right, and people cannot hear the difference. So that is actually an important thing you have to know when you want to develop such algorithms, that at some point you don't need to care about the fine structure anymore. Just use some noise and get the statistics right and you're fine. Now, I want to talk also about different implementations and different ways to actually produce sound signals for headphones and what their different perceptions are. So I want to start with the reference, if you like, with the gold standard, and that is, of course, the real world. So, for example, here you have me speaking and you're listening, or in that example, you have a guitar playing and somebody listening in a room. And, of course, you can localize the guitar, you can get some idea of how big the room is, how reverberant the room is, and everything is fine. Now, you can actually reproduce this experience quite well by putting some microphones in the ears of a listener, or an artificial head, if you like, and recording the left and right microphone signals, and then playing it back via headphones. So, who of you has heard the virtual barbershop demo yet? 1, 2. If not, it's on the material there. There is a link to the virtual barbershop demo. Please have a listen. It really works well. And it is actually a binaural recording, possibly with some post-production applied to it. The makers of that video, which are related to a hearing aid company, they don't want to tell too much what they did, but I inquired and they told me it is, the base of it is actually a binaural recording. Yeah, of course, with that binaural recording, you also get the same thing. You can localize the the sound source, and you get information about the room. Now, I skipped the next 2 points because they're not relevant at this point. If you do the same, I mean, if you try to reproduce the same thing, but just with HRTFs, so you make a recording of the guitar alone, and then spatialize it by applying the HRTFs, these really short signals of 3 milliseconds, to it. Well, you are doing spatialization, obviously, but you're not doing it well. Because what you typically get is that the guitar comes really close to your head. It's still outside the head if it works well, but it's not far and really close. And you have no room information whatsoever. So that is, it is 3D audio, but not really good 3D audio. And then the extreme thing is a stereo mix. So you record the guitar, you apply a gain for the left channel and a gain for the right channel, and well, what you get is basically something playing like just above your head, behind your head, inside your head, whatever your personal experience is, but it's definitely very close to the head. It's not outside your head anymore, clearly. Now, to go more deeper into the acoustical side, I want to talk about the room impulse responses. So we talked about the head-related impulse responses before, or HRTFs if you like the other acronym. But the other side, I mean, that is the head side of it. The other side is, of course, the environment, or in this case here, is the room. And so if you have a room and a microphone and a source in it, you have the source emit a perfect impulse. What you measure at the microphone is the so-called room impulse response. And it looks as it's shown here on the slides. So it's basically one impulse, and then there are a few reflections, and it kind of fizzles out into some late reverberation tail. You can do the same thing also with an artificial head or with microphones in the ears. Then you get something that is called the binaural room impulse response, which is basically the whole thing in 2 channels, with one channel for the left ear and one channel for the right ear. And again, to make the relationship with the head-related impulse response, if you leave away the room now, you actually get the head-related impulse response, which is this really, really short signal there on the slides at the bottom in the middle, which is about a factor 1,000 shorter than the whole binaural room impulse response. And of course, if you want to do good spatialization, good 3D audio, what you need are these binaural room impulse responses, because they contain all the information about the head and about the room. And so let's look a little bit more in detail at these binaural room impulse responses, because they are actually not that difficult to model properly. You just have to know which parts are important. Because, I mean, like the naive approach, it would be simply to say, yeah, let's measure binaural room pulse responses for every combination of source and listener position inside the room. And, well, you easily get into the hundreds of thousands of positions you would have to measure. So it's like completely unfeasible, at least completely uneconomical to do this. But if you know what you have to model, of course, it gets much easier. So the first part in a binaural room pulse response is the direct sound. It's basically the equivalent of the head-related transfer function, or HRTF, because it is it's everything that happens before any reflection is coming back from any wall. So it's like what happens in an anechoic environment. Then, of course, we have reflections, and you can see them quite well in most binaural room pulse responses. So they are basically, again, HRTFs or HRIRs placed at different delays for different directions, which correspond to the directions where the the reflected sound comes from, and possibly also convolved, or normally also convolved with some kind of filters which correspond to the absorption at the walls. Or if you have reflections that come very late, also the absorption of the air. Because if you have a reflection that comes from 1 kilometer away, it will be low-pass filtered a lot because the air absorbs the high frequencies. And then comes the third component, which is the ambient reverberation, which is basically also reflections, but the messy type of reflections. And the interesting thing here is that these kind of messy reflections, they don't necessarily appear only very late in an impulse response, but they can also appear quite early simply because you have reflecting objects that are scattered around the room. Like a room like this here, it has a lot of small surfaces. Take the projector, the table, the chairs, and so on. Everything reflects. So maybe the reflection from this chair here back to me comes before the reflection of any wall. So if you add up all these small reflections coming from small surfaces, they also contribute to some kind of ambient reverberation, which is actually not technically late reverberation, but like early ambient reverberation or early diffuser reverberation. And so, of course, that is something that is nice to model as well. It improves the quality if you do this properly and not follow some very simple physical model, which normally doesn't consider this. And yeah, of course, I'm doing that as well in my algorithms. Now, so these were the physical parts. How does this correspond now to the perception? The direct sound, as I said before, it's just an HRTF. So basically, it gives you a directional information. And since it is the direct sound, it gives you the information of which direction the source is relative to yourself. That should be pretty logical. These early reflections that you have seen in the impulse response, in the binaural room impulse response, they give you an information about the room size and also about your position in the room and the source's position in the room. Even though, unless, except for some people that are really good at this, like blind people that know how to do some kind of echolocation, normally you don't consciously perceive the position. But the information is there. I mean, there are blind people that do like, I cannot do it. They make like a really snappy sound with their mouth. And from the reflections, they can say which type of room they're in and that maybe there is a wall in front of them or even a chair in front of them. So they're like doing the same thing as bats. So kind of amazing what the brain can do. Well, we cited people which have not undergone a special training for this, normally cannot do it, but still we normally get a certain feeling at least of the room size. So for that, of course, it's important to also model early reflections. And finally, the diffuser reverberation or ambient reverberation is important for the feeling of envelopment. So it's this being inside feeling which is caused by this diffuse reverberation. And if you combine these different things, especially the reflections and the envelopment, or the basically, well, technically it's actually the level difference between the direct sound and the reverberation plus the reflections, you get an estimate of the distance. So the brain actually combines the different informations from direct sound, early reflections, and diffuse reverberation, and from this tries to estimate how far a sound source is. And so that's another reason why you should actually model all of these things and not just direct sound, for example, if you just use HRTFs. And something now about the quality perception. So these were more like quantifiable quantities that are perceived, like distance and so on. But how about the quality? How do we feel being inside a certain virtual environment? And the quality of realism or comfort in a virtual 3D audio environment depends on multiple factors. So there is, for example, the quality of the HRTFs. Do you have a small set of HRTFs and then jump between them, or do you interpolate very smoothly? These are all, they are perceivable. You hear if it's well done or not. Another topic is the individualization of HRTFs. So because, of course, the head shapes and the ear shapes, outer ear shapes, they are different for different people. And you normally get a good result by providing, let's say, 3, 4, 5 different HRTFs, and people just choose the one that works best for them. But you could even do better by doing real individualization, tuning the HRTFs until the person says, yeah, now it's really very realistic. Then, of course, for the reasons I explained on the previous slides, sound reflections are important, room size, etc. Diffuse reverberation is important, distance perception, envelopment, etc. Another topic is also the continuous movement of the sources. So you basically, when you move a sound source in your environment, or you even just turn your head or move yourself in the environment, these binaural room pulse responses, they need to change continuously. If they don't, it's not as natural as it would be as if they would change continuously. And finally, like if you actually have some visual feedback, which certainly you have with VR goggles, you see the sound sources, and when you turn your head, the positions change. That helps a lot too. It helps the quality, the perceived quality of the audio as well. Which actually includes the head tracking. Another thing that is related to my demos, which you can, by the way, see on my stand, is if you, even in a 2D interface, if you move the sound sources around yourself, it actually is better than if somebody else moves it for you. Or, I mean, if you see it, it's also better than if you don't see it. If you just have the audio of some sound source moving around you, it's not as good as if you actually see on the screen, I'm here, and the sound source is moving like this. So this feedback and manipulation aspect is quite important, as it just helps the perceived quality. And last but not least, actually the content is really important. If you have, in the extreme limit, you have sinusoids. You know, I mean, if you have had some classes in signal processing, if you take a sinusoid and you apply a filter to it, you still get the sinusoid. It's just amplified and phase shifted. So all the information contained in the binaural room pulse response is like projected onto two quantities, phase and gain, which don't give you any spatial information at all. So basically, if you have sinusoids, you cannot do 3D audio with it. But if you have like some chirpy sounds, like, or some noisy things, these things work really well, and you can place them in space really well. And also like impulsive sounds, they allow you to hear more delayed reverberation, which is also good for estimating, for example, the room size and so on. So thinking about what kind of audio works well, if you have the possibility to change the audio, is certainly a good idea. And last but not least, one thing that is important to remember is that all these aspects, they basically reinforce each other. So maybe you have a project where some things you cannot do. I mean, for example, very often you cannot do HRTF individualization because, well, you bring out an app and people that you don't know are downloading that app, or you present something here at this virtual reality forum and you don't know who are your visitors and you don't have the time to go through some individualization procedure. So you don't have that. But if you do all the other aspects well, that helps a lot. And maybe the people still really like your 3D audio experience, even though it's not individualized. Now, what is the 3D verb technology that I'm actually presenting here? It's basically an acoustic environment simulation, which does, I hope at least, as many things correctly as possible. So I'm positioning the sources which with completely interpolated into HRTFs. Oh, I didn't translate that from French to English. I'm also working on an HRTF individualization procedure that hopefully comes out maybe this year and next year. And I'm simulating acoustic reflections with it. Only recently I added diffuse filters for it. So imagine you have an outdoor environment and you have a reflection coming from a forest, which if you're living here in Switzerland, you have certainly heard it already, because you know, all the people in the military, they have to go to some shooting practice every couple of years, I think, or maybe every year. And these shooting ranges, they're often close to forests. So you hear a gunshot and then you hear this coming from the forest. And it's a little bit gritty. It's like a gritty kind of noise coming back from the forest, which is basically the forest reflection impulse response. And it's really long. It's a couple of seconds long. So now, specifically for modeling outdoor environments, I added the possibility to include these long FIR filters to model long reflections that are coming from really big objects like forests. Diffuse reverberation, of course, I added that because it was basically the subject of my PhD thesis, so I spent a big effort on getting that right. And yeah, basically all the components of the binaural room pulse responses that I'm applying with the 3D verb algorithm, they're basically made on the fly. So the reflections are computed on the fly, the direct sound is computed on the fly, and all the filters are completely adapting as they have to, as they would in the real world as well. Of course, it's aimed at real-time manipulation, which actually allows also to do head tracking, which of course you have with VR goggles. There you have the head tracking already included. If you don't use VR goggles for head tracking, of course you need at least a gyroscope mounted somewhere to the head. And last but not least, the algorithm that I developed, it's optimized in two directions. It's optimized for the perceptual quality and for the CPU performance. So just to give you a rough idea of the CPU performance, already about 5 years ago, I could simulate more than 20 sources with like really basic devices at that time already, like the second generation iPhone. Nowadays, I didn't do a new calculation like this. I didn't try to put hundreds of sound sources in, but I can assure you, you can at least do 100 sound sources simultaneously with my algorithm. Because it's really optimized also for many sound sources, not just doing one sound source as efficiently as possible, but doing many sound sources efficiently, even though it's maybe not the most efficient you can do with just one sound source. But anyhow, who wants to have virtual reality with just one sound source, right? And yeah, combining all these different aspects to really get a convincing effect. Even if you don't have individualization, you don't have head tracking, etc. And most of it is actually C code, so it's adaptable to new platforms really easily within a few days, I would say. And currently I have implementations that I'm maintaining for ARM, both 32-bit, 64-bit, and for the Intel processors. I don't know how interested you are to get into the technical details of the algorithm. Just to say one thing, basically I have different blocks for diffuse reverb, early reflections, and HRTF, applying HRTFs. And what I'm doing is that I'm, for example, bundling all the diffuse reverb. I'm bundling all the reflections coming from a certain direction. So basically, if you add one source, the audio buffer for one source, it just has to be copied in the right places to be afterwards in the output stage be processed by the correct diffuse reverb and by the correct reflection directions. So all these things that are kind of expensive, like applying diffuse reverb and applying reflections, they're actually done just once. They're not done for each source individually. So that helps to get the thing really efficient with a lot of sources. Now I see I should come to the end of this talk. Just to talk a little bit about the philosophies and about auditory VR. Basically, you can have different philosophies of what you want to do with audio in VR. You can apply just HRTFs. You say, I just care about the directions, which is really simple, is really efficient. But of course, it's unrealistic too, because you're basically modeling an environment that doesn't have reflections, and normally you see visually that there are objects that would actually reflect in the real world. Then there is also another approach, which is not my approach. It's to do a physical simulation. So you can do very sophisticated models to actually get the sound propagation in the room physically correct. And of course, that is the closest thing you can do to reality, but it's normally pretty costly. And to some extent, some things you really have to do individually, especially if you're calculating like multiple reflections in all directions. You have to do that for every source again. So you cannot take advantage of this bundling that I'm doing. So what I'm doing is basically I look at the impulse responses I should apply based on measurements or based on physics simulations, and then model those elements that are perceptually relevant. And well, I think it's a pretty good compromise because it allows to do all sorts of simplifications and efficient implementations, and at the same time it's still perceptually quite good. I mean, it gives you the feeling of being inside the room and so on, even though it may not do the physics as accurately as other methods do. Now, the last thing, 3D audio as an auditory VR. If you think about it, well, probably VR normally for you is goggles and so on, but if you think about it, actually 3D audio is kind of virtual realities, but not for the eyes, but for the ears. So with no specific hardware, just headphones, you can actually recreate the impression of being inside some environment just with your ears. So if you close your eyes, you have actually virtual reality. There are some nice aspects about this. You don't get motion sickness from it. At least I didn't manage to do that. And in the audio domain, I mean, that's not specific to 3D audio, but audio doesn't have this uncanny valley effect. This kind of, well, it is a real environment, but it's not real at the same time. In the auditory modality, we are less critical, I would say. If we hear a voice and it sounds natural, then that must be it, right? So at least maybe if the voice is synthesized, yes, there is maybe something equivalent to the uncanny valley, but relative to the 3D aspects of it, I'm not aware of any uncanny valley effect for 3D audio specifically. Yeah, the conclusions, I think I don't need to say so much about this. So, of course, high quality binaural audio is more than just the HRTFs. I've been talking about this the whole time now. You have to approximate multiple perceptual cues because we're kind of integrating the different cues. And well, 3D audio, 3D verb, my algorithm does these things quite efficiently, also with a reasonable quality perceptually. And coming soon is a version for outer environments. And yeah, of course, even though I don't have a Unity plugin out yet, there is no reason why it should not be possible to integrate, right? So I'm definitely looking into it. If you can convince me that there is actually a market for, let's say, a Unity plugin of my algorithm, I will also start working on this. So yeah, thank you very much for your attention.